function of different galaxy properties, and it worked really well. Okay, so we didn't have any new free parameters. We just sort of put in this physical recipe, and wow, it actually worked. There should be a long list of other people who have also done very similar things, both with semi-analytic models and with hydrodynamic simulations, including Benedict Deemer, who was here until recently. So back in 2014, people say that that we don't make predictions, but sometimes we do make predictions. So here was a prediction of the density of molecular hydrogen as a function of redshift. These were two different recipes for partitioning the gas into molecular and atomic hydrogen. And mass functions of molecular hydrogen back to redshift 6, just from our, whatever our favorite model was. So since then, a very amazing machine called Alma has gone on the sky, and in cycle 4, there was a large program approved. So I am a co-I on this program to do an untargeted survey of a very small region of the sky, 4.6 square arc minutes. But importantly, a lot of the work with Alma up until this point had been, oh, here's a ULERD, let me go look at it. Here's something I found in some other way, let me go look at it with Alma. So this is just whatever you point at is what you get, right? So we did an untargeted search for, and of course, different lines of CO are visible at different redshifts. And the nice thing about this field, this is the Hubble Ultra Deep Field, so of course there's gorgeous and very deep ancillary data, including IFU data from the MUSE instrument. So again, lots of papers have come out in the last year. I encourage you to go on arXiv and read them. There's a whole bunch about to come out as well. I just want to give you one paper that was led by Gergo Popping, my former student, now on the staff at ESO, in which he took these predictions from our Santa Cruz SAM and from Illustris TNG, post-processed to calculate the amount of molecular and atomic hydrogen in the galaxies. And so we could look at the mass of molecular hydrogen versus stellar mass. And interestingly, so the pink is the SAM, the blue and the yellow are just two different ways of measuring the gas mass in TNG, sort of ignore it. Basically, they agree with each other, which is interesting, the SAM and Illustris. And at redshift 0, they agree very well with the observations of H2 masses in galaxies. Again, not surprising because they were sort of tuned, though not entirely. Now let's look at what ASPEX sees. So at redshift 1.4, 2.6, 3.8, here are points from ASPEX and also from another survey called FIBS. And you can see that neither model seems to predict enough galaxies with very large reservoirs of molecular hydrogen, and getting worse as we go back in cosmic time. So we can plot this in terms of a mass function. So here are the predicted mass functions from the models. Here are the observed constraints on the mass functions, and also from another survey called Cold Z, which is a larger area, less deep. And you can see there's a significant discrepancy. One thing that we did was to take 1,000 ASPEX area light cones through our box to study cosmic variance, field-to-field variance. And so that's shown at 2 sigma by the shaded regions. So there seems to be a pretty significant tension, especially around a redshift of 2, with these observations. So what could be the reason? Of course, I'm surprised that no one has asked me already, but of course you have to convert from the observed CO line, whatever that is, to CO 1 to 0, and then to a mass of molecular hydrogen. That's of course uncertain, but in order to resolve this tension, you would need alpha CO of around 0.8. So if you know alpha CO in your head, you know that that's a very extreme value. It would be a bit surprising and interesting if that were the case. You might also say, well, maybe your recipe for partitioning gas is wrong. Even if all of the gas in the ISM were in the form of molecular hydrogen, there would still be a problem. So more probably, this is a really beautiful data set for helping us to refine and improve our modeling of star formation and/or stellar feedback.
What about metallicity? Because we know at high redshift
Yeah.
metallicity is lower, so it would be even harder. I mean, for me it was even surprising because
Yep.
it would be even harder to form even H2, but especially CO.
So the models, of course, track chemical evolution, and the recipe is metallicity dependent. But though, the modeling could be wrong, the dependence could be wrong. So yes, I agree, metallicity is a very interesting thing to look into. Okay, so I'm going to go super quickly through the last part of my talk. In fact, I'm just going to go straight to an advertisement because I want to leave at least a few minutes for questions. So we can try, Julio already pointed out, yes, converting from what you observe in these CO lines to molecular hydrogen mass is very tricky. So we're trying to forward model now, do all of the PDR modeling to actually estimate the luminosity of the whole CO ladder and also of ionized carbon of C+. You can read these papers by Gergo Popping showing our comparisons in that space with detections of individual sources by Alma. I'm going to skip all that, sorry. To the advertisement, which is we're trying to make predictions for a technique called intensity mapping, which is fun for me to bring up here because I first heard about it many years ago from Avi, and I thought, Avi, you're crazy. There's no way we'll ever, CO is so faint, there's no way we're ever going to be able to do it. Now there's like multiple experiments that are doing this, not only for CO, but also for C+, of course for 21 centimeter, for H alpha, for many lines, okay? So what we want to do is use this machinery to make mock intensity maps that contain all of these lines, all of these tracers, which has never been done, but we basically have the machinery to do this. However, it's very hard. Again, these processes depend on the structure of the ISM on the scale of giant molecular clouds and smaller, and these surveys are going to do hundreds, thousands of square degrees. So even with semi-analytic models, we've succeeded in making a 2 by 2 square degree mock intensity map, which is shown here. It's going to be very hard. It's going to be very hard. Okay, I want to stop. You can ask me about using machine learning to try to do this even faster, and I'll leave this here and take your questions. Thank you.
So I was wondering if this logo of the dragon chasing its tail symbolizes the circular reasoning that's inherent in this type of modeling, right? Where you're using the observations to tune the subgrid physics, and then using the code to predict the observations. And I see what you're doing. You're trying to get.
We're actually trying to break that cycle. So it was not intended to symbolize that.
But those simulations that you have of the subgrid physics have their own subgrid physics in them.
That's true.
Where do you come to some level of truth or something? What can you say? Now I understand this.
It's a great question, and I think it's a philosophical debate that we could have for many hours. But perhaps we can validate these small scale simulations using observations on those scales. Right? And then we can see if we get the global observations right. And then I think it's no longer circular.
Well,
So
I think
it's
a good project.
Okay, yes. As I like to say, I don't expect to see the end of this project in my career or lifetime.
After spending so many decades in cosmology, I realized that the barriers, the fact that we have 5% of the budget in barriers, serves an extremely important purpose for theories, because you shove all the uncertainty into the barriers. Whenever the theory doesn't agree with observations,
It's
you
the
change the
periodic
barriers.
physics, that's absolutely right.
But in principle, there is another knob that you can turn, which is the dark matter.
Yes, of course.
Do you think, do you include that in your program, or do you think we could constrain dark matter somehow?
That is not part of this program because it's already very large and very hard. But I think it's extremely interesting to think about that interplay. And I think that currently, if you vary the dark matter, but then you tune your subgrid to match observations, then it's almost impossible to learn anything about dark matter from observations variance. But if we actually succeed in building this scaffolding that goes up from, from the small scale processes, then I think you could do that project.
Like very dark matter, you mean changing from cold dark matter to something?
Yeah, to these, there's like a whole stable of exotic dark matter models, as you know.
Can I ask a variant of the question that Eric asked, which is rather than going downwards, going upwards in scales in these simulations? How far up from, starting from these toolbox simulations, and presumably it's going to be near on impossible to get a fully predictive model that goes all the way to the large scale structure of the universe. But do you think there's a
That's what we're trying to do.
But,
that is what we're trying to do.
But
yeah.
is there a particular scale to which we can be confident that we'll be able to get a reasonable handle of things on and without worrying about that, something's going to break or something like that?
Well, our goal is to build up to scales like the current, sort of couple hundred megaparsec boxes. That's our goal. Maybe a few years off. But, obviously we have to build it up step by step, right? We want to do an individual Milky Way, then we want to do, maybe a Zoom.
I guess the goal is even beyond that. If you understand, given the dark matter halo properties, what galaxy history, what galaxy is, all periods of time, then you can